All right, it's Tuesday here. We're going to continue our treatment of Chapter 25, which deals with electric potential and electric potential energy. We're going to quick review of electric field and the electrical potential energy. Then we're going to get into this concept called the electric potential, which is voltage. Um, and then we're going to apply it to a parallel plate capacitor and 2-point charges. We're going to do that tomorrow, so we probably won't get that far today. So a couple modifications here. Homework 7, I'm not going to be able to get it online until probably Saturday, late morning or so. So it will not be due until next Friday night, the 19th at 11:59 p.m. Quiz 2 will be Monday the 15th during the synchronous lecture, and that will cover homework 6. So before we get into the electric potential, I think it's good to go back and review the electric field and electric potential energy here. So recall that if you have two charges, Q1 and Q2, right, they exert forces on one another, right? And we can use Coulomb's law, and we can calculate the force that Q1 exerts on Q2 and the force that Q2 exerts on Q1, equal and opposite forces. But when you start getting into more than a couple charges, it's a lot easier to describe the interactions between charges by introducing this concept of the electric field, which we denote by E. Okay? And charges create this electric field. Okay? Charges alter space by exerting electrical forces on other charges that are in that region of space. And we describe the effect of these source charges using the field E. And so to find the electric field at some location in space, recall from chapter 23 that we took this positive probe charge Q0 and we put it at some arbitrary position, and we calculate the force that all of the source charges would exert on this charge Q0. We get that force, and then we divide by this charge Q0, and it's the force per unit charge that a positive charge would experience at that location in space. And so, for example, suppose that the charge would experience a force of 10 newtons due to all the other source charges. And suppose the charge is 1 coulomb. Okay, that's obviously a little big, but just for simplicity with numbers, then the force per coulomb would be 10 newtons. And so if we had 2 coulombs of charge, that charge would experience 2 times 10, or 20 newtons. If we had 3 coulombs of charge in an electric field of 10 newtons per coulomb, that would experience 30 newtons of force, and so on. And so we take this positive probe charge, we move it all around space, we calculate the total force on that positive charge at each location, and we can get the electric field due to all of the different source charges. Now you're going to see a much more pragmatic means for getting the field in a little bit. This isn't really how you would do this in practice. It would take you forever. But in principle, this is what you can do for a small number of charges. And so if there's more than one source charge, we would add up all the contributions using the principle of superposition. And that means either by summing them up if the charges are discrete, or by integrating if we have a continuous charge distribution. And we've done much of that in chapter 23. Here's an example that we went over. So just suppose that, again, for the single point charge, so we can stick our positive probe charge Q0 at any location, and we know that the force between the two charges would be KQ, the source, times Q0 over the square of the distance. So now we get that. We get the magnitude of the force. We divide it by the magnitude of the probe charge, and we get the electric field due to a positive charge is kq over r squared. And we derived that in chapter 23. That's the field due to a point charge, okay? And if you notice, there's no sign of the probe charge q0 in here because we divide out by it. So the field depends only on the source charge, which in this case is just q, and on the distance of any charge from that source charge. Okay, so that was the electric field for a positive charge. And since the field lines point in the direction of the force experienced by a positive charge, which would be repulsion from this positive charge, the field lines point outward away from a positive source charge. And you can do the same thing if you have a negative source charge. You replace q by negative q, and you would get that the electric field is negative kq over r squared. And these field lines would point toward the negative charge because the positive probe charge located anywhere would be attracted to this negative source charge. And so this was the field due to a single point charge that we discussed in the last chapter, chapter 23. Then you can go on, and if you have many different source charges, we can apply the equation of the field due to each source charge, kq over r squared, and you can add up all of the fields due to each of the source charges, add them up like vectors, and we get the total electric field using what's the superposition principle, which means summing to get all of the vectors. And if you recall from chapter 23, this can be a little painful, right? Because you have to add up all the vectors, then you have to get a magnitude of the total vector, and you have to get the angle. And so this gets kind of clunky when you start getting beyond, 2, 3, 4 charges. So we're going to come up with a much better way, or simpler way to get the field in this chapter. But this is how we did it for multiple charges. Then we had introduced this concept of the electric field lines, right, where at every point in space you could draw the magnitude and the direction of the electric field, but that also gets pretty cumbersome. And so we got into this concept of these electric field lines where the spacing between the lines is proportional to the field strength, right? So the field strength is closer to plus q, and so the lines are closer together, and they're further apart as we go away. And so these electric field lines are usually much easier to visualize and to work with than to draw the electric field at every point in space. And so that was the electric field. Then we introduced this concept in the last lecture called electrical potential energy, where we discussed that if you calculate the work done by the electric field in moving some charge over some distance delta r, that the work is equal to the negative change in this quantity called the electric potential energy, okay? And this behaved very similarly to the gravitational potential energy. Remember MGH from Physics 1. So this was much easier to deal with than dealing with the electric field because it's a scalar. So if you want to calculate the electric potential energy due to several charges, it was just adding up scalars and not having to deal with the magnitude and the angle like we did with the electric field, which is a vector. And so then we went over the example, an important example where if you have a uniform electric field, in other words, where the field magnitude and the direction are constant, like in between the plates of a capacitor, then we calculated the work, and if you have the positive charge here moving from plus to minus, the the force on the positive charge is in the same direction as the field, and that's in the same direction as the displacement. And so cosine of the angle between the field and the displacement is 1 because theta is 0. They're in the same direction. And we derived that the work was equal to the force, which is Q times E, times the magnitude of the displacement times the cosine of theta. And if the field and the displacement are in the same direction, then theta is 0, cosine of theta is 1. And if the field and the displacement are in the opposite direction, then theta is 180 degrees, and cosine of theta is -1. So some people, will like to keep the sine out here and ignore the cosine of theta. I like to keep it here because that way it guides me to the correct sign always. Okay, you always look for the angle between the electric field and the displacement. And in our case, in this class, it's almost always going to be 0 or 180 degrees, and so this is always going to be either 1 or -1. Once you calculate the work, then the change in the electrical potential energy is just the negative of that. And so for a constant electric field, then it's equal to negative Q times E times the magnitude of the displacement times cosine of theta. And then we went over an example here. So here's a positive charge, and the positive charge is going to be attracted to the negative plate, right? So it's going to go to the left in this figure. And in this case, the angle between the displacement and the electric field is 0. Cosine of 0 is 1. And so the work done by the field is QE delta S, right? In other words, it's positive work. And since the change in electrical potential energy is the opposite sign as work, this leads to a decrease in the potential energy. And so one easy way to remember is that potential energy always decreases when the charges move downhill, right? When they're moving from positive toward negative, because that's where they want to go. However, and so that's the potential energy decreases and the kinetic energy increases. Now, if you move the positive charge and you try to move it against the gradient, right, because you're trying to push it toward the positive charges, then it's going to gain potential energy. Work is negative. It's going to increase potential energy, and it's going to slow down. Okay, so it can decrease in kinetic energy. So charges always gain potential energy. If they're going against the gradient, they gain potential and they lose kinetic if they're going uphill. And if they're going downhill, they lose potential and they gain kinetic. And so this was a quick review of the electrical potential. Then we calculated for 2-point charges. We could calculate it using, here you have force 1, one exerts a force on 2, 2 exerts a force on 1, and in this case, they're repelling each other, right? And so the force and the displacement are in the same direction, and so cosine of theta is 1, because theta is 0, and it just becomes the integral of the force times the displacement, and then we integrated that, and we got that the potential energy at some separation r between the two charges was equal to k q1 q2 over r. And that looks exactly like the force, right, except it goes as 1 over r, and instead of 1 over r squared, and it's a scalar instead of a vector. And then once we have this, if you have that, we can apply superposition. And so if you have a bunch of point charges, then you can calculate the interaction energy between each pair and simply add them up as scalars to get the total. And so it's much easier to work with energy than it is to work with forces because they're scalars. Um, so now, just like we defined the electric field as the force per unit charge, we're going to define this quantity V called the electric potential. And this is not to be confused with the electric potential energy, U. So this is what is defined as the potential energy per unit charge at a given location, due to all of the other source charges. So just like the electric field was the force per unit charge due to all the source charges, this electric potential V is the electric potential energy per unit charge exerted on our little positive probe charge due to all of the other source charges. And so we define that with the symbol V. Now, you've probably all heard of this, but maybe not in this context. So if you have a battery here, this battery says 1.5 volts, okay? This is a double A battery here, okay? So, or this is a D cell battery, sorry. So what does 1.5 volts mean when the battery says 1.5 volts, or you put a 9-volt battery in your smoke detector? What does 9 volts mean? Well, what this means is that between the two terminals, which in this case the plus terminal and the minus terminal, the potential difference delta V is 1.5 volts. Or in other words, the potential energy, the change in potential energy of a positive charge Q going from the plus to the minus is 1.5 joules per coulomb, okay, is the change in the potential energy per unit charge in going from one location to another. So delta V is 1.5 volts between the two terminals of the battery. And so often we call this the voltage, or the voltage difference between the two leads of the battery. So when we say potential difference or delta V, it's what we typically call the voltage, the difference in the voltage between the 2 points. So if we go back to here, this voltage or potential difference is equal to the potential energy per unit charge. Or in other words, how many joules per coulomb of potential energy the charge has for every coulomb of charge at that location. And it's kind of unfortunate because the units for V are volts, which is given the symbol V. And so both the variable name and the units have the same symbol. Okay, so for example, if the voltage at a given point is 3.4 volts, we would write V as 3.4 V. Unfortunate, yes, but that's the way everybody does it, and so we'll have to get used to it in this class. And so, for example, if the voltage or the potential at a given point is 1 joule of, for example, if you have 1 coulomb of charge and the potential difference, the potential is 2 joules per coulomb, then the potential energy of 1 coulomb would be 2 joules per coulomb times 1 coulomb, or 2 joules. If you have 2 coulombs of charge and the potential energy, the potential is 2 joules per coulomb, then the 2 coulomb charge would have 4 joules, the 3 coulomb charge would have 6 joules, the 4 coulombs of charge would have 8 joules. And so this potential at a given point is the amount of energy per charge Q per coulomb that a positive probe charge would have at that point due to its interaction with all of the other charges. Okay, so these source charges create a potential V at a given point in space, regardless of whether the probe is there or not. The probe is there to measure the magnitude of this potential. And so to find V, we can do the exact same thing that we did with potential energy. We can stick a positive probe charge Q at the location. We calculate its interaction energy U electric due to all of the other source charges. We sum up all the scalars to get the total electric potential energy. We divide by the magnitude of the probe charge Q, and we get the potential V at any point due to the other source charges. Now, similar to U, which is the electric potential energy, only differences in the potential between points have physical meaning, okay? So only delta V has meaning. And so we can set the location of V equals 0 wherever we want. So for household wiring, for example, the Earth's ground is usually the point that we call V equals 0, and all of the other potentials at any other location are referenced to the value at ground. So you might say, okay, well, why are we introducing yet another means for quantifying the interaction between charges? And the answer is, again, it's similar to electric potential. V is a scalar, so it's a lot easier to add up the contributions to V due to the different source charges than it is to calculate electric fields and then add up all the vectors, get the magnitude, get the angle. That's clunky. There's two other reasons why we deal with V a lot. In fact, more than U electric and more than E. And it's one main reason is that voltage can be measured. Okay, for example, we can take a voltmeter and I can put a lead at the positive terminal and another lead of the wire at the negative terminal, and I can measure the potential difference very easily using a meter, a voltmeter. And so it's a lot easier in practice, in the real world, to deal with V, the voltage, than it is to deal with the electric field. The second reason is once we get V, we can get E very easily by the spatial change in V. So if we can calculate V at all these different points, we can get the electric field very easily. So it's just a lot easier to deal with the voltage than it is to deal with the electric field or electric potential energy. And they're very easy. Once you get V, you just multiply by Q to get the electric potential energy. And we're going to come up with a real simple relationship between V and the electric field. So usually in practice, we're dealing with voltages and not electric. We can get electric fields through simple equations relating the two. So recall from the last lecture that if you have energy conservation, remember that for charged particle moving under the influence of other source charges, that we can write that energy is conserved. In other words, the change in the kinetic energy of the system plus the change in the electric potential energy is 0, right? And so we can write that the initial energy, which is kinetic plus potential, must equal the final. Okay, we can write the same thing in terms of the potential V if we just note that U is Q times V. So we can write delta U is equal to Q times delta V, and we can get conservation of energy expressed in terms of the potential V, which again is much easier to measure. So this is conservation of energy applied to in the terms of voltages. So let's look at the signs here, because again the signs are the hardest thing to remember here. And so if you look here, positive charge, if it goes toward increasing potential, remember positive charges want to go downhill toward decreasing potential. So if the positive charge is forced to go against the gradient here, or to go uphill toward higher potential, the positive charge will gain potential energy at the expense of kinetic energy. It will slow down if you try to take a positive charge and get it to go uphill. Okay, and so one example here is take our battery here. So suppose you've got the positive charge and you started off at the negative terminal of the battery, which is right here. Okay, and we try to move that positive charge over to the positive terminal here of the battery. Okay, well, it's not going to want to go that way, right? Because there's all these positive charges here that are repelling it and trying to push it back. And so if you're trying to get positive charges to go uphill against the gradient, they're going to lose kinetic energy, right? And they're going to gain potential energy. They're going against the gradient. Okay, so the positive charges will gain potential energy. And this is exactly the source of this, which we'll try to get into later, is a chemical reaction inside the battery, which tends to give this positive charge the energy that it needs to push it over to the positive plate so that we can keep the potential difference between the terminals. Now, what about a negative charge here? So if you've got a negative charge and we try to go in increasing potential, a negative charge is going to speed up, right? If you try to, for example, here, suppose you take an electron and you try to push it over to the positive plate. So in other words, you take a negative charge and you try to move it toward a region of higher potential. Okay, well, the electron is going to be attracted to all these positive charges, right? So it's going to gain kinetic energy because it's going to be attracted to these positives, and it's going to lose potential energy. And so recall with positive charges, they're going to lose potential and gain kinetic as they go from positive to negative potential. And for negative charges, they are going to gain potential and lose kinetic as they go from positive to negative, because they don't want it, right? They're going against the gradient. You have all these negative charges over here, and the negative charge is going to be repelled. So they're going to gain potential, and they're going to lose kinetic. So let's do an example here. So suppose we have an electric field, and suppose we have a charged particle that has a charge of 3.0 times 10 to the negative 5 coulombs, and it has a mass of 1.8 times 10 to the negative 5 kilograms. And suppose we release it from rest at point A. And suppose that the potential at A is 25 volts greater than at B. So the potential at A is more positive than the potential at B. Okay. Well, what's going to happen here? It's going to be the positive charge is going to be going downhill, right? It's going to be going from higher potential at A to lower potential at B. So it's going to gain kinetic energy, it's going to speed up, and it's going to lose potential energy. And so what we want to do in this first part here is we want to calculate the speed of the particle at B. Okay? So to do this, the easiest way, always when you see these types of problems, energy conservation should be the first thing you think of. Okay? And so what we can write is that since VA is 0, the change in potential kinetic energy, which is 1/2 the final kinetic minus the initial kinetic, and the initial kinetic is 0, plus the change in potential is equal to 0, right? So in other words, the gain in kinetic energy is the loss in potential. Okay, and we can solve this for the final speed VB. We plug in numbers. Q is equal to 3 times 10 to the negative 5 coulombs. VA minus VB is positive 25 volts because A is at a higher potential than B. And then we divide by the mass, and we get that the speed of the particle by the time that it gets to point B is 9.1 meters per second. Okay, so positive charges moving from higher to lower potential are going downhill, so they're going to gain kinetic and they're going to lose potential. Okay? Just like if you drop a ball and the ball drops, the ball is going downhill toward lower potential energy, and so it's gaining kinetic energy. Okay, what about in this case? Okay, suppose that we take this same situation here, but suppose that instead of a positive 3 times 10 to the negative 5 coulombs, the charge is negative 3 times 10 to the negative 5. And then let's suppose that we start it at point B and we send it to the left. So we take a negative charge and we send it right to left. Okay, what will its speed be at B? Okay, so let's look at this here. The negative charge is going toward A, so it's moving toward higher potential. It's going from lower to higher. Okay, and so negative charges going lower to higher, that's downhill for them, right? They want to go toward the positive charges here. And so the negative charges are going to gain kinetic and they're going to lose potential. So let's calculate, in this case, what the charge would be, the speed would be at point A. So in this case, again, we can write energy conservation, right? Change in kinetic plus the change in potential energy is 0. In this case, it's VB that is 0 in this case because it's starting at B with 0 speed, so that's 0. So VB is 0. I'm sorry. VB is the potential difference. I'm sorry. VB minus this VB is 0 right here. I'm sorry. So it's 0 minus 1/2 MVA squared plus Q times the potential difference is 0. We can solve for VA. Okay, now here we've got to be careful with the signs again, right? So point A is higher potential than point B by 25 volts. So VB minus VA is negative 25 volts in this case because A is higher than B. Okay. However, the charge is also negative, so Q is negative 3 times 10 to the negative 5 coulombs. Two negative signs cancel, and the particle has the negative charge would have the same speed when it gets to A as a positive charge would have if we started it to the right at what it would be at point B. So again, just keep track of your signs. I think that's the hardest part, and just draw the picture if you have. Well, you should draw the picture always. So let's conclude with just a small exercise here. So suppose that we have a proton, positive charged particle, and we stick it at a location that we're calling V equals 0. Okay, so we're calling point B the location of 0 potential. Okay. Now again, remember we could, since only the potential differences matter, and point C is 100 volts higher than B, and point A is 100 volts lower, we could equally well call point B 1,000 volts, point C 1,100 volts, and point A 900 volts, but we're choosing just arbitrarily to call point B 0 because it's only the differences in potential that matter. So suppose we started at rest at point B, okay? Afterwards, which direction is the proton going to go? And is it going to go at steady speed or increasing speed? or is it going to do nothing? Is it just going to remain at rest? Okay, well, that probably isn't going to remain at rest, right? The proton is going to want to go in which direction? Um, it's going to want to go toward negative. So I screwed up here. I've got to fix this. This actually should not be C. The proton is going to want to go from higher, it's going to want to go downhill toward lower potential. So in other words, more positive to less positive, or 0 to more negative. And so the proton is going to go to the left, right? It's not going to want to, it can't go uphill if you started at rest. You're not giving it any energy. So it doesn't have the energy to go uphill. So it's going to go downhill. Just like if you started a ball at rest, the ball is going to fall downward. Sorry about that. Let me fix that here. Okay. So the answer that we rule out B, it's not going to remain at rest. We can rule out D and E because it's not going to go toward more positive potential. So that leaves us with B or C. Oh, sorry, my answer was right, sorry. So then the question is it going to go with steady speed or increasing speed? Okay, well, it's going to be losing potential energy, right? It's going from 0 to negative 100 volts. So it's going downhill from higher to lower potential energy. And so it must be gaining kinetic energy, or in other words, the speed is increasing. So the answer is that the particle will move toward A, the positive charge, and it will move with increasing speed. So positive charges, if left at rest, will go downhill. Okay, so just for kicks, what if this charge were negative? Okay, what would it do then? Well, the negative charge is going to want to go toward a more positive potential. And so the negative charge, just like the positive charge wants to go downhill, the negative charge wants to go uphill, right? It's more attracted toward the more positive potential. So the negative charge would go to the right toward higher potential. It would be losing potential energy and gaining kinetic. So negative charge would go to the right toward higher potential. Positive charge would go to the left toward negative potential. So I think that's enough today. So we will tomorrow go into some specific applications like potentials due to parallel plate capacitors and single and multiple point charges. And then we're starting to get closer toward applying this all toward electronics in circuits once we start getting into the next chapter. So I realize that this is pretty abstract stuff. You need a cup of coffee sometimes. We're getting there. We're getting close to the applications of it. So have a good night, and we'll see you tomorrow.